Alex Alexander here, database expert of Alchemy. I decided to record a training video to help with our existing environment configuration. We're using several components for our Postgres installation. So we have the Postgres SQL database, DRBD, Pacemaker, and part of the Pacemaker configuration is a Corosync. So just briefly to cover our existing, the way our architecture is working. So we have a pool of reporting users connecting to the Postgres databases. And on Postgres databases side, so we have two node configuration with DRBD copying data from active node to the passive node. We also have a virtual IP, so the users are connecting to the virtual IP, and that virtual IP practically determines which one is the active server. So the entire configuration, once again, there's a Postgres SQL database. This is DRBD that replicates data between the nodes. There's a Pacemaker component that monitors the individual components within those nodes, such as Postgres SQL database, disks, and so forth. And of course, there's a Corosync component of Pacemaker that relays the messages between the nodes. So the way failover is accomplished is that when primary database here would fail, Pacemaker would detect the outage, relocate, dismount the file system on the primary database, mount the file system on the standby database, and once this process is completed, start up the PostgreSQL, relocate the virtual IP, and hence the virtual IP is relocated. It's also going to relocate the database connections in turn. And this is how failover is accomplished basically. It's also DRBD traffic would be reversed if we're performing the switchover. So the two ways are possible. The automated failover in case of database outage, and planned switchover in case there needs to be some kind of maintenance task to be performed. The users could be switched from one node to another node. Now the question would be, why would select DRBD versus using Postgres streaming replication? Well, because the requirement is to have data in two data centers. Hence, DRBD is being used locally in the local data center. And then Postgres streaming replication is used to propagate the data from the local cluster to the remote cluster in a second data center. So Postgres streaming replication practically moves the data. That's why DRBD was selected, because there is no way to use streaming replication locally and streaming replication across a data center, because that would require the databases have the capacity to subscribe to two masters, which is not existent today. And so it's a very fast and proven configuration. DRBD been out there for quite some time. Streaming replication is fairly new, but the combination of those services will definitely assure the high availability. As I mentioned previously, we have several components to our configuration. So we have that Postgres database, we have DRBD, Pacemaker, and a Corosync. So we'll start reviewing those components and how they interact together to deliver a high availability Postgres solution for Alchemy. So we'll begin from the lowest level components and then we'll focus on the highest level components, such as Postgres application itself, and review the configuration parameters. And we'll start basically from the network configuration. Hence, we are using DRBD and we're using Pacemaker. So one of the most important aspects is to have bonded interfaces configured. And the bonded interface, practically what it does, it bonds several network interfaces into single interface. So you can have multiple network cards bonded in the single interface. What that provides redundancy, and it also provides high availability, so, and performance in turn. So we'll take a look at network configuration. And so what we have here on both of those boxes just a second. So what have here in both of those boxes, so we have a bond 0 interface right here. And the bond 0 interface, this is a bonded interface. So this interface is used to move the data from node 1 to node 2. So the data is being copied over the bonded interface, and also the pacemaker component performs the monitoring over that bond 0 bonded interface. So the two physical network cards that bonded in a single interface. So it provides high availability, and it also provides performance. Hence, the application such as DRBD is capable of using bonded interface to move the data from node 1 to node 2. So usually the bonded interfaces are prerequisite for any type of high availability configuration. Hence, it provides redundancy, like I mentioned, and performance. And then we have additional interfaces such as those, if you see here, EM1 on both boxes, and those are external interfaces. This is where the application users, in our case, now let's take a look at the diagram. This is the interface where the porting users will come in through the external interface. So we have two separate interfaces, the bonded interface for the DRBD configuration and the external interface for the application users. Usually it's a good idea, so this way the heavy traffic from DRBD will not be interfering with the existing application users. Now, having said that, we'll probably begin actually practically looking at individual components. So let me cue this part and clear the screen so we can focus on this part. S, and I'm going to sudo s in this box also. So, and to view the DRBD configuration, basically you can do cat proc DRBD. There you go. As simple as that. Proc DRBD. And if you look at this configuration here, so what we have in DRBD, typically in DRBD you have the primary node and you have a secondary node. As you can see, this DB01 in this case is actually a primary node according to DRBD output, and the node 2 is a secondary node. So it's a secondary node, and the other things that's showing here is basically both of those nodes are up to date. So it indicates it's up to date and indicates it's up to date. So that indicates that both of the nodes, DB01, DB02 are up. DB01 is a primary node. That means the data is being replicated synchronously from node 1 to node 2. So it's DRBD is working. And if we look at the processes, we can see DRBD processes are up and running here. And here on DB02, we once again have DRBD processes running and functioning. Because this DB01 is a primary box, that means Postgres would be running on this box also. So we'll quickly check for it. And you see, we can tell there's a Postgres process is running on the primary box, and there's no Postgres process running on the secondary box. Another important aspect is how the file system is configured in order to have DRBD functioning. So what we have, if you can see, that's varlib MySQL. It's a logical device. So it's a LVM configured logical device, and the same thing as a node 2. This is the same thing. So we used LVM to partition the devices and allocated a dedicated device to Postgres configuration that is formatted in XFS file system. So we're using XFS to house our Postgres configuration. Now, if you look at those boxes, because DB01 is a primary database at this moment, you see that there is no varlib PG-SQL mount on DB02. Well, that's because Postgres in our configuration operates in active passive format. So in active format, the file system is only mounted on a box where Postgres is up and functioning. So when the primary box would fail, it would dismount the file system on primary box, and it would mount the file system on a secondary box. Also will start the Postgres and relocate the virtual IP. So this is basically how it functions. So the box, the active server always has the file system mounted, and the passive server doesn't have the file system mounted. And now it's a big difference here between Veritas cluster server or any type of shared configuration is that each one of those servers has a copy of the data. So DB01 has a full copy of the data and DB02 has a full copy of the data, except the file system is not mounted on DB02. So it'll become mounted when the outage would be detected. So that will continue reviewing the DRBD configuration that we have in place. And the way it works, like once I mentioned, we have logical volume configured, and this logical volume right here is dedicated to serving PostgreSQL. Sorry, actually this is the logical volume. So this volume right here is serving dedicated to service PostgreSQL. So let's quickly take a look at LV display. So what we have here, we have a logical volume, vol PG, that is dedicated to PostgreSQL, 2.5 terabytes in size. So this is the actual logical volume, and the same deal is here. So we have exactly the same configuration. One very important aspect when hosting clustering configuration is to have exactly identical configuration, preferably. Hence, both of those nodes are completely interchangeable. So there is really no notion of master-slave node. This is just active and passive node. So DB02 being a passive node and DB01 being active node. So there's a logical volume configured. And now on top of this, in DRBD configuration, you cannot just go ahead and mount that logical volume. So what you're actually mounting, if we look at the file system here, what you're actually mounting, you're mounting a DRBD device. So that logical volume is not even formatted with XFS. That logical volume configured with DRBD, and DRBD volume in turn is formatted in XFS. So how does that happen? So we go to DRBD configuration directory. .d. So, and DRBD configuration directory is stored in etc drbd.d, and we have two files here. We have a global configuration file that's basic parameters are stored, and we have a second file is actually the DRBD resource file, hence the extension res, the resource. So we'll take a look at this file, and this is where the actual device configuration happens. So if you look at this, I named the device Postgres right here, and then you have a device name itself, dev drbd. That's this is any name you can assign to it, by the way. And then disk, this is where the volume configuration comes in. If you noticed, this is a volume name, so that's where the volume is being configured. So you're basically mapping logical volume to DRBD device, and that's a metadata stored internally. And of course, the last several sections indicate the members of the DRBD configuration. So we have the primary node here, and we have the secondary node with the addresses. So primary, secondary node. So we're providing the IP addresses for the nodes that are members of DRBD. Now here, DRBD.d, if you notice here, it's exactly the same configuration on this box. So for all practical purposes, once you create the configuration file, the same file is copied to the secondary box. So the second file is copied to the secondary box, and for all clustering purposes, it's basically identical configuration. And if we look at this box right here, you'll notice that DRBD volume is mounted to varlib PG SQL. So that's practically how the entire configuration works. So you create the volume, you map it, you configure it, and what it does, it begins copy data from DRBD device to DRBD device from node 1 to node 2. So it copies what it does. It copies blocks of data. So it's, as a matter of fact, the entire replication and copy process is completely transparent to the Postgres. And as far as Postgres is concerned, it doesn't even exist in that perspective. It just communicates with DRBD. Very good technology. You know, it provides the uptime and high availability. So this is the mount points once again, and that's how the entire process is functioning in the configuration files. So having reviewed the DRBD configuration on our Postgres cluster, we'll just do a basic review, recoup of the information that we covered. So to watch the status of DRBD, we just simply issue cat proc DRBD, and sorry, that will show the actual current DRBD configuration, primary, secondary, and the same things here, proc DRBD. You can see secondary, primary. The configuration for DRBD is stored in etc drbd.d, and that's where you can see the actual resource files. There you go. That's our DRBD configuration working over the bonded interface. So as far as DRBD goes, this is as simple as that. The mounting, TC first tab, the mounting of the file systems and in turn DRBD devices is accomplished by the Pacemaker. So the Pacemaker has various resources configured, so we don't have to manually mount or dismount a specific resource. Pacemaker itself is going to mount or dismount any specific resources. And then I mentioned before, we're using XFS file system for our resources. And there is a dedicated logical volume and dedicated DRBD device, the way it's configured. So having covered that subject, we're going to transition to next topic and focus on the Pacemaker. And the Pacemaker is a tool that provides the high availability and monitoring. So Pacemaker, as you configure the various resources in the Pacemaker begins monitoring, and it also will take action. So when specific resource fails, such as Postgres database, Pacemaker will perform the entire reconfiguration. So it will dismount the DRBD, mount it to the standby mode, relocate the virtual IP, and start up the Postgres and relocate the virtual IP. So we'll take a look at the CRM, and the way you interact with Pacemaker is using the CRM command line. So if we enter CRM, you can enter a help command here, and it will tell you the list of available commands. So you can do, for example, status. And the status would show you basically the status of current CRM configuration. CRM, we enter the same here. Status allows you once again to view the current configuration. So what we have here, we have, like I mentioned, master slave configuration. We have primary master database DB01, and we have secondary database DB02, and also shows you various resources that we configured. And in order to have Postgres high availability, basically it boils down to three basic resources. So we have the Postgres FS. That's a file system. This is basically the DRBD volume file system. We have DBIP. This is a virtual IP address. And of course, we have Postgres SQL. So we have three resources in our Pacemaker configuration. Once again, Postgres file system, and you can name it technically these resources anything you'd like to name them. So we have Postgres file system, virtual IP, and Postgres database. So that's simple as that. And Control D, and I'm going to Control D out of this. And then you can obtain the same information by using CRM mon command -1. It'll give you the status of the resources. Mon -1. There you go. That'll give you the same resources. It tells you. Now, the interesting thing is, when operating in a clustering configuration, is practically you cannot just go ahead, stop, and start the Postgres database on your primary node. Because if you stop the Postgres database, it'll essentially, what you'll do, it'll trigger the failover. And if you trigger the failover, basically it'll relocate the virtual IP. Basically, by manually shutting down Postgres database, what you'll do, you'll trigger the actual outage. So the way you interact with a clustered configuration here, if you need to restart Postgres or perform some kind of maintenance task and things like this, you always use the CRM tool. And CRM tool allows you to interact with a cluster. So basically, the clustering term is very important to understand. Within this DRBD cluster, you always use CRM tooling to perform all your tasks. So you always interact with CRM. So having covered the cluster configuration, we'll focus on how to administer the existing cluster using the Pacemaker CRM interface. So CRM is a standard interface to manage Pacemaker. As a matter of fact, all of those commands could be performed on any cluster member, on DB01 or DB02, really makes no difference. So, but CRM is the actual interface, and you can issue the help command here and say status. It will show you the status of the current cluster and current resources. So we have the file system, there's the DRBD file system right here. We see the IP address and the Postgres database. Now the question is, like if let's say if I made the changes to the Postgres parameter and I'd like to restart my Postgres database, if you do it directly by going to Postgres, it's basically what you're going to do, you're going to trigger a failover. So the way to accomplish restarting any of the resource, not only Postgres but any resource, is through the CRM. So we enter the resource menu. First let's check to make sure that our instance is up. POS. So, and here you can see that we have our PostgreSQL processes. So that indicates the PostgreSQL database is up. And so with that we'll go to CRM menu, go to resource menu. So, and status. Look at the status, so PostgreSQL is up, so all the resources are up. And we can do stop. And the resource name, in our case we're trying to stop PostgreSQL. There you go. If we exit this menu now, drop POST. You can see that Postgres database is down now. So to bring the Postgres database up, we go to CRM menu, enter resource, and you can do status again to see your resources, and then start. PostgreSQL. So, and exit the console. Let's check on the status. Sorry. There you go. Postgres database is back up. So that demonstrates how to interact with CRM resource to bring up and down Postgres database and any specific resource they'd like to bring down.